Okay, let's unpack this. Imagine trying to teach a robot to do something that, for a human, is incredibly simple, almost instinctive, like opening a kitchen drawer, pulling open a microwave door, maybe sliding a panel. Sounds easy, right?
Yeah, it seems trivial for us.
But what if it's, a drawer the robot has never seen before?
Yeah.
Or maybe a microwave door with a really stiff hinge.
Exactly. And this isn't just about the robot moving its hand to a point in space. It's much more complex.
Right. It needs to make contact, apply just the right amount of force continuously, throughout the movement.
And crucially, it has to understand how the object is behaving and responding under that force. That's the key part.
Okay.
Precisely. This is a class of problems in robotics called sustained contact manipulation. It's quite different from, say, simple pick-and-place tasks.
How so? Different how?
Well, with pick-and-place, you basically grasp an object, then move it rigidly. But with sustained contact, you're continuously interacting with the environment. You're applying force, often dealing with objects that have articulated parts.
Articulated parts. Like joints.
Exactly, joints that allow them to move relative to their base. Think doors that swing, drawers that slide out, things like that.
And getting robots to do this robustly, especially when they see objects they didn't train on, or even if you just want to use a different robot arm.
Yeah.
That's been a really significant challenge, hasn't it?
Oh, absolutely. A major hurdle. Traditional methods, well, they often fall short. They can become brittle. They struggle to generalize.
Which is exactly where our deep dive for today comes in. We're plunging into a new framework that aims to tackle this head on.
That's right. The framework is called FLEX.
FLEX.
It stands for Force-Based Learning for Extended Manipulation. It's a novel approach proposed by researchers at Tufts University.
Okay, Tufts University. And we're looking at their paper.
Yes, we're dissecting their research paper. The title is FLEX, a framework for learning robot-agnostic force-based skills involving sustained contact object manipulation. Quite a mouthful, but it captures it well.
It certainly does. So our mission today is really to get a deep understanding of FLEX. How does it think about this complex problem, sustained contact manipulation? What's the technical approach it takes to actually learn these skills? And how does it handle that generalization challenge? Unseen objects, and maybe most intriguingly, transferring the learned skill across totally different robots.
That transferability is a big claim.
Yeah, what makes this approach potentially a significant step forward compared to what's come before? Let's jump in and explore.
Sounds good. So let's really focus on the core problem first.
Yeah.
Sustained contact manipulation. As you highlighted, it covers tasks where the robot keeps continuous physical interaction with an object or surface to achieve some goal.
Right, like opening drawers, sliding windows.
Pushing objects along a surface, operating levers, interacting with hinged appliances like washing machines or ovens.
Yeah.
These aren't tasks you finish with just one precise placement.
No.
They involve this dynamic interaction and continuous force application all the way through the task.
Right. It's like you're guiding the object along its intended path, but you have to keep applying force the whole time. It's not just getting to a position. It's about the process of that interaction.
Exactly. And this is why it presents such significant difficulties for robots, especially compared to, say, just grasping a static object.
What are the main difficulties then?
Well, the first major challenge is needing precise force control. If a robot's only programmed for position control.
Just moving to coordinates.
Yeah. It might try to move its end effector to a certain coordinate, but if an object resists that movement, say, a stuck drawer, the robot could just exert way too much force.
Damaging itself. Or the object.
Potentially, yes. Or just fail to move it at all. It needs to sense that resistance and apply force appropriately, not just blindly follow a position command.
And the object's own mechanics, that becomes critical too, right?
Absolutely crucial. A drawer slides linearly, a door rotates around a hinge. The robot has to interact with the object in a way that respects these underlying mechanical constraints.
You can't just push anywhere. Pushing sideways on a drawer won't open it.
Exactly. Pushing perpendicular to the track does nothing useful. Pulling radially on a door handle isn't the efficient way to swing it open. You need to apply force correctly relative to the joint.
And those dynamics can vary a lot.
Hugely. Object dynamics are often complex, especially for these articulated objects, and they can vary greatly from one instance to another. Think about a brand new, stiff hinge versus an old, loose one. Or an empty, lightweight drawer versus one full of heavy stuff.
Right. Trying to perfectly model those dynamics in the real world for every single object a robot might bump into sounds,
Well,
Impossible.
It's incredibly difficult, often totally impractical, and then you add the robot's own complexity on top of that.
The robot's action space.
Yeah, it's high-dimensional action space, coordinating, dozens of joint angles, or precisely controlling a 6 DOF end effector in Cartesian space while also applying and controlling force.
Yeah.
It's a very tough control problem.
So given all these difficulties, what have people tried traditionally? And why do they struggle with generalization?
Well, a common approach has been using robot-centric reinforcement learning, RL, or maybe imitation learning, IL.
Okay.
In these methods, the robot learns a policy that directly maps its sensory inputs like camera images or its own joint states straight to its own actions, like joint torques or maybe end effector velocity commands.
That sounds powerful in theory.
It can be for specific tasks in very controlled environments, but these methods typically require massive amounts of training data, and critically, that data has to be collected on the specific robot doing the task.
Ah, I see the problem. If the robot learns to open this specific drawer by learning a sequence of its own joint movements,
Mm-hmm.
that learned sequence is probably completely useless for a different drawer, right? Or even if the robot's base position changes slightly, or if you try to use a different model of robot arm.
Precisely. That's the significant generalization gap the FLEX paper is really addressing. The learned skill becomes tightly coupled, almost glued, to the specific robot's kinematics, its dynamics, and the exact configuration of the training set up the environment, the object instance.
So transferring those learned policies to a new object, even a slightly different one, or definitely to a different robot arm, often means you have to start the training all over again.
Pretty much from scratch, yeah. Which is incredibly costly and time-consuming in robotics.
Okay, so that's RL and IL. What about methods that rely more on models, like model predictive control, MPC?
Right, MPC is another powerful technique.
Yeah.
It works by using detailed mathematical models, physics models, dynamic models of both the robot and the object.
To plan ahead.
Exactly. It plans optimal actions over a future time horizon. And if you have a perfect model, MPC can achieve really impressive results. Smooth, efficient motion.
But that's the catch, isn't it? Perfect model.
It's the Achilles heel, definitely. Especially in complex, unpredictable, real-world scenarios. Getting and maintaining accurate dynamic models for arbitrary objects, maybe deformable ones or things you've just never seen before, it's often just not feasible.
And even small errors in the model could mess things up.
Oh yeah. Even small modeling errors can lead to performance degradation, instability, or outright failure. So while MPC is great in simulation, or maybe for known, well-characterized objects in a factory setting, it really struggles with the kind of open-world variability you get when a robot needs to interact with all sorts of different articulated objects out there.
Okay, so we have methods that are either really tied to this specific robot and need tons of data, or they need these perfect models that are just super hard to get in practice. That really highlights the need for, well, a different way of thinking, a different paradigm to get these robust, generalizable manipulation skills, especially for the sustained contact stuff.
It absolutely does. And this is where FLEX comes in with its fundamental departure from these traditional approaches.
Okay, here's where it gets really interesting then, where FLEX introduces its core conceptual shift. Instead of focusing on the robot's exact movements or trying to perfectly model everything, FLEX proposes these two powerful ideas: learning manipulation skills in force space, and crucially, decoupling the policy learning process from the specific dynamics of the robot that's going to execute the skill later.
Exactly. Let's unpack that first idea. Learning in force space. Imagine you're teaching, say, a child to open a door.
Okay.
You don't tell them, okay, move your hand exactly 6 inches forward, now rotate your wrist 70 degrees, then move your elbow precisely this much. That would be ridiculous.
No, you'd say pull the handle or push the door.
Right. You teach them the action of pulling or pushing the handle and then applying force to swing the door open. You're teaching them about the interaction with the object itself, not the specific, muscular commands to achieve it.
Okay, so translating that to the robot. Instead of telling the robot the desired spatial, pose the position and orientation of its hand, FLEX is basically telling it, apply this specific force vector, like apply this much force in this exact direction, right at the point where you're touching the object.
Exactly. The action space is fundamentally different. Instead of this complex 6 or maybe 7-dimensional pose or velocity command space, which is tied to the robot's joints or its end effector, the policy just outputs a much simpler 3D force vector. Force X, Force E, Force A.
And how does that help? Just simplifying the action space. Fewer dimensions to explore during learning, I guess.
That's a big part of it, yes. The learning algorithm has a much smaller action space to search through, but it's actually more profound than just dimensionality reduction.
Okay.
By outputting force, the policy is directly focused on how to interact with the object to get the motion you want. It inherently discourages actions that would cause the robot to, say, lose contact.
Because you can't apply force if you're not touching it.
Right, so it significantly reduces the amount of useless exploration during the learning process, where the robot might just flail around or detach from the object.
And, like we were saying earlier, applying force directly seems to align better with how the object actually works, its mechanics. A drawer slides because of force along its track. A door swings because of torque around its hinge. The way the object moves when force is applied, that feels like a fundamental property of the object itself, almost independent of who or what is applying that force, as long as the force is applied correctly relative to the object's structure.
That's the absolute key insight. Learning in force space captures these fundamental object dynamics directly. The learned skill becomes about how do I apply force to this kind of joint to make it move, rather than how do I move my specific arm to open this specific instance of a drawer.
Which leads perfectly to the second core idea then.
Yeah.
Decoupling. Training the policy in a totally robot-free simulation environment.
This is perhaps the most powerful aspect when it comes to generalization across different robots. The policy isn't trained to output robot joint commands or even end effector poses relative to the robot space.
No, it's outputting the desired force.
The desired force to apply to the object. The training environment is abstract. It simulates the object's physics, how it responds to applied forces, but it doesn't need to include the specific kinematics or dynamics of any particular robot arm.
Okay, so you train this force-based policy once in this simplified simulation.
Yes, focus solely on the object's behavior under force.
And then, because the policy outputs are these force vectors relative to the object's contact point, you can take that exact same learned policy and just transfer it directly to a completely different robot platform. Like you can train it conceptually and then run it on a Panda or a UR5 or a Kinova without retraining the core manipulation skill itself.
Precisely. That is the revolutionary potential they're claiming. Because a policy has learned how to manipulate the object using force, independent of the robot's specific mechanics, it becomes inherently robot-agnostic.
Right.
As long as the robot you want to use is capable of executing force control, which thankfully most modern collaborative robots are, you can potentially use the same learned policy.
That would dramatically cut down the cost and complexity of deploying these skills on different hardware.
Hugely. And there's a bonus, too. Removing the complex robot physics from the training simulation makes the training process itself significantly faster and computationally cheaper. You don't need to simulate all those robot joints and links.
That makes perfect sense. It aligns with that diagram in figure 1 of the paper, doesn't it? Where you see the learning happening in this abstract force simulation and then arrows pointing out to different robot arms successfully doing the task.
Exactly. Figure 1 gives you that high-level visual roadmap. Learn the decoupled force skills once, then transfer them out.
Okay, let's get into the nuts and bolts then. How does FLEX actually achieve all this? The paper lays out the architecture in figure 3, breaking it down into 3 main parts that happen sequentially when a robot meets a new object. First, the force-based skill learning.
Right, that's the offline training part.
Then, interactive joint parameter estimation.
That's when the robot interacts with the object.
And finally, robot execution.
Putting it all together on the robot. Let's start with part 1, force-based skill learning. This is where the core manipulation policies are learned, and like we said, it's done offline, in that robot-free simulation environment.
The focus is purely on the object and how it reacts to forces being applied to it.
Correct. Now, they frame the problem using reinforcement learning, but they make a smart choice. They structure it as 2 separate Markov decision processes, or MDPs.
2 separate ones. Why?
Well, one MDP is tailored specifically for objects with prismatic joints, think drawers, sliding cabinet doors, things that move linearly.
Okay.
And the other MDP is for objects with revolute joints, things like hinged doors, microwave doors, stuff that rotates.
Why split them? Couldn't you just try to learn one giant super policy that handles both types of joints?
You probably could, theoretically, with an extremely complex policy network and maybe vast amounts of data, but it would likely make the learning problem much, much harder.
Because the motions are so different.
Fundamentally different geometric and dynamic behaviors, yeah. Prismatic motion is linear. It's a translation along an axis. Revolute motion is rotational. It's about rotation around an axis. By creating separate MDPs, they constrain the learning problem for each policy. Each one only has to focus on the specific dynamics relevant to its joint type. It just makes the learning process more tractable and efficient.
That makes a lot of sense. So what information does the learning agent actually see in this simulation? What defines the state for these object-centric MDPs?
The state is defined carefully to capture information about the object's configuration and the interaction point, but importantly, it's decoupled from the robot's own state.
Okay, give me an example. For the prismatic one, the drawer.
Okay, for prismatic objects, if you look at figure 2A in the paper, the state vector includes the direction of the joint axis. They call it HP. It's basically a 3D unit vector pointing in the direction the drawer slides.
Right.
It also includes aept. That's the displacement of the current contact point relative to the initial contact point projected onto that joint axis HP.
So it tells the policy which way the track of the drawer is pointing and kind of how far along that track the current push or pull is from where it started.
Exactly. It knows the direction of movement and the progress along that direction. The whole state vector is just those two things, HP by key. Very compact.
Okay, very object-focused. What about for revolute objects, like a door hinge?
For revolute objects, visualized in figure 2B, the state includes the direction of the joint axis again. They call it HRR, a 3D unit vector for the hinge axis, and it also includes VT.
VT.
VT is a 3D vector. It represents the projection of the vector going from the joint's origin, the center of rotation, to the current contact point, projected onto the plane that's perpendicular to the hinge axis HR.
Okay. So that captures where the contact point is relative to the hinge itself and sort of within the plane that the door swings in.
That's a good way to put it. It tells the policy about the lever arm and the position in the rotation plane. The state vector here is HR, VTE.
Again, this feels very abstract from a robot's point of view, but very intuitive if you're thinking purely about the object's mechanics. It's all about the object's geometry and where you're interacting with it relative to its joint.
Precisely. And this object-centric state representation is absolutely key to the whole decoupling idea. The policy learns based on these abstract object properties, not the robot's own joint angles or base position.
Okay, so that's the state. What about the action? What is the policy output?
The action space is actually shared across both MDPs, both prismatic and revolute. It's simply a 3D force vector, let's call it F, applied to the object surface at the contact point, and there's a maximum magnitude allowed, 8 eta. This 3D force vector is the direct output of the policy network.
So the policy sees this abstract object state and decides, okay, based on this, I should apply this much force in this specific direction right here at the contact point. How does it learn which force vector is the right one? That must be the reward function's job, shaping the behavior.
Exactly. The reward function is crucial. They designed it to be dense, which means the agent gets feedback at every single simulation step. This really helps the learning process converge much faster than if it only got a reward at the very end.
Okay, so what does the reward encourage?
The core principle is to reward the agent for making the object move efficiently in the desired direction, which, for these tasks, is typically opening it. So the main part of the reward is tied to the object's displacement, how much it moves, specifically in the direction of the force that was just applied.
So if you push a drawer forward and it actually moves forward, you get a positive reward contribution.
Correct.
But if you push sideways and it doesn't really move forward much because of that push, that part of the reward is low or maybe even negative.
Exactly right. The paper gives the equation, which looks a bit dense itself. R egg scolds plus I goal, R goal, but only if egg scolds, otherwise it's X goals. Let's break that down to get the intuition.
Please do.
Okay, axer is simply the magnitude of the object's movement in that little simulation step. How far did it actually move?
Got it.
Then, cosine is the cosine of the angle between the applied action, which is the force vector, the policy output, denoted A in their formula, and the object's actual movement direction.
Okay, the cosine. So if the force is perfectly aligned with the way the object moved, the angle is 0, cosine is 1, maximum positive contribution there.
Exactly. You get the full reward based on the distance moved. If the force is exactly opposite to the movement, angle is 180 degrees, cosine is -1, you get penalized.
And if you push perfectly sideways, perpendicular to the motion, angle 90 degrees.
Cosine is 0. That component of the reward is 0. Your force didn't contribute to the useful motion in that step. So this cosine term is a really elegant way to measure the efficiency of the force application, isn't it?
Yeah, it seems like it. It's asking, are you actually getting motion because of the force you applied? And is that motion in the right direction?
It is. It directly incentivizes applying force in the direction that most effectively moves the object along its allowed joint motion. Now, that if EQ is RO part,
What's that?
that's just a simple filter. EQ represents the change in the object's joint state, like how much the drawer extended or the door angle changed. This if statement basically ensures the agent only gets the positive reward components when the object is moving out, opening, increasing area key, rather than moving in, closing, assuming the task is to open it.
Okay, so it doesn't accidentally reward closing the drawer slightly.
Right. And finally, that IGOR term. IGOL is an indicator function. It's 1 if the goal is reached, no otherwise. Our goal is a large positive bonus reward. So you only get this big bonus when the object actually reaches the goal state, like being opened past, say, 80% of its limit.
That provides a really strong signal to guide the agent towards finishing the task.
Definitely. It's a clear, dense, and intuitive reward signal for learning efficient, sustained contact.
Okay. And the learning algorithm they use to optimize this reward is TD3. Any particular reason TD3 is a good fit here? Or is it just a standard choice?
TD3, which stands for Twin Delayed Deep Deterministic Policy Gradient, is a pretty robust state-of-the-art choice for this kind of problem. It's an off-policy actor-critic RL algorithm, and it's known for being quite effective in continuous action spaces.
Which is exactly what we have here, outputting that 3D force vector.
Exactly. TD3 also includes some nice techniques like using two critic networks, delaying policy updates, and adding noise to the target policy actions during updates. These things help improve stability and prevent the policy from exploiting errors in the value function estimates, which can sometimes be a problem in complex continuous control tasks like this manipulation stuff.
Interesting detail. The policy network itself predicts two things separately. Predicts the force direction and the force scale. Why split that?
Yeah, that's a neat architectural choice. The final policy output is formed by combining a predicted 3D unit vector for the direction and a predicted scalar value between 0 and 1 for the scale, or magnitude relative to the maximum.
And then they multiply those together and scale by the overall max force.
Right. The paper suggests that separating the prediction of direction and scale actually improves control precision and makes the learning more efficient. It kind of allows the policy to separately reason about where it should push or pull the direction vector and how hard it should do it relative to its maximum capability, the scale factor. It potentially gives finer-grained control than just trying to predict a single 3D vector where the magnitude and direction are inherently coupled.
Interesting. And one more thing about the training. The policies are trained to be contact agnostic. What does that mean in practice during this training phase?
It means that within a single training episode, the specific point on the object surface where the simulated force is applied isn't fixed. It's actually randomly sampled from a predefined region.
Like anywhere on the drawer handle, or maybe anywhere on the front panel of the drawer.
Exactly, or maybe along the edge of a door. By doing this, it forces the policy to learn a strategy that's robust to variations in the exact point of contact.
So if the real robot later grasps the handle slightly differently or pushes the drawer panel a bit off-center,
the learned skills should still be effective, because the policy has learned how to apply force correctly relative to the object's joint mechanics, regardless of the precise contact point within that allowed region. It definitely enhances the policy's robustness for real-world transfer, where grasp points might naturally vary a little bit.
Okay, so after potentially millions of these simulation steps, using TD3, optimizing that dense reward function, you end up with two expert policies trained in this abstract robot-free world. Opera for prismatic joints and 4 for revolute joints.
That's the outcome of part 1.
But now, the big question. In the real world, when a robot walks up to a completely new cabinet it's never seen before, how does it know which policy to use? Prismatic or revolute?
Yeah.
And how does it even know what the object's specific joint parameters are? Like where the axis is?
Ah, yes. That brings us neatly to part 2 of the framework, interactive joint parameter estimation. This is the absolutely crucial step that enables these learned policies to actually work on arbitrary, unseen objects in the real world. The robot can't just assume it knows the object type or its exact joint configuration beforehand.
Okay, so how does it figure this out? Does it need, like, a massive database of 3D models to recognize, that's a Model 734 cabinet. It has a prismatic joint here?
No, and that's a really key point of this approach. It doesn't need to recognize the object semantically as a drawer or a microwave. Instead, it uses its onboard sensor, specifically an RGBD camera.
So it gets depth information as well as color.
Yes. It uses the camera to perceive the local geometry around where it intends to interact, generating partial point clouds of the object. Then, it employs a pre-trained grasping model. The paper mentions one called AO Gray SP. But others could potentially be used along with a standard motion planner to first get a secure grasp on the object, maybe on a handle or an edge.
Okay, so it grabs onto it first.
Once it's holding the object, or at least in frame contact with it, it performs what the paper calls, well, what we could call a kind of probing dance.
A probing dance. Tell me more about this dance.
It's not really dancing. While maintaining contact or its grasp, the robot applies small controlled forces in a few predetermined directions. For instance, it might push forward slightly, then pull backward, maybe push left, then right, perhaps even try a small vertical push or pull.
So it's deliberately, gently trying to wiggle the object.
Exactly. It's actively interacting with the object, trying to elicit a little bit of motion or maybe feel the resistance to understand its underlying structure and how it wants to move.
So it's gathering information about the object's mechanics through interaction, not just passive observation.
Precisely. This short, probing interaction creates a brief trajectory of the robot's end effector positions in 3D space. Just a few points showing how its hand moved while applying those small forces.
Okay.
The robot analyzes this recorded trajectory data to infer the object's joint type. Is it moving like a prismatic joint in a line or a revolute joint in an arc? And also to estimate its specific parameters.
Parameters
Like the location and direction of the joint axis, the line for a drawer, the hinge axis for a door. And for revolute joints, it also needs to estimate the radius of rotation.
How does it make that inference from just a few points on a short trajectory? That sounds tricky.
It employs a statistical technique called maximum likelihood estimation, or MLE.
Okay.
Here's the idea. For each potential joint type, prismatic and revolute, the robot calculates how likely it is that the end effector trajectory it just observed was generated by an object with that specific joint type, assuming some estimated parameters for that type.
So it's like asking, how well does a straight line model fit this data? And how well does a circular arc model fit this data?
That's a great way to think about it intuitively. It's essentially fitting those two different geometric motion models to the observed trajectory data and seeing which one provides a better explanation for the points it recorded.
And how does it find the best line or the best circle parameters to use for that comparison?
They use some standard geometric analysis techniques. For an initial guess at the axis direction, they might use principal component analysis, PCA, on the trajectory points. Then they refine these initial guesses by solving least squares optimization problems.
Okay, least squares, minimizing errors.
Exactly. For a prismatic joint, the optimization tries to find a line defined by an origin point, PO, and an axis direction vector, HP, that minimizes the sum of the squared distances between each observed trajectory point, API, and its closest point on that proposed line.
So it's minimizing how much the trajectory deviates from being a perfect straight line along the estimated axis HP.
Precisely. The math equation, ADPIAU-AAP, is basically calculating the squared length of the perpendicular vector from each point to the line and summing those up. Minimizing this finds the best fitting line.
And for a revolute joint, it's similar but trying to find the best fitting circle.
Correct. For a revolute joint, the optimization aims to find a circle defined by a center point, P and a radius, R, that minimizes the squared error between the actual distance of each trajectory point, P from the proposed center P and the proposed radius R.
Making sure all the points are roughly the same distance from the center.
That's exactly. The term they minimize, a BFE, gets smallest when the points lie close to a circle defined by P and R. The least squares process finds the P and R that minimize this error for the observed trajectory data.
Okay, so the robot does its probing dance, collects the trajectory points, runs these two separate optimizations, one assuming prismatic, one assuming revolute, to find the best fit parameters for each type. Calculates the likelihood of the observed data under those best fit parameters for each type, and then just pick the joint type, prismatic or revolute, that resulted in the highest likelihood score.
That's the decision process, yes. Whichever model explains the observed motion better is chosen as the inferred joint type.
What about objects that are more complicated, like maybe an oven door that hinges down but also slides out a bit, or something with a more complex linkage like some cabinet doors have? Does this handle multiple degrees of freedom?
That's a really important question to consider. And the short answer, based on the paper, is no, not directly.
Right.
The framework presented here specifically focuses on objects with simple, single degrees of freedom, either purely prismatic or purely revolute.
Okay.
The interactive perception approach, fitting these simple linear or circular models and the subsequent policies, OMTAR, are designed explicitly for this scope. This covers a lot of common articulated objects like standard drawers, typical doors, basic appliance doors.
But not everything.
Not everything. Handling objects with multiple coupled joints, or more complex non-standard kinematics like those parallelogram linkages, would likely require a more sophisticated probing strategy. You'd need to excite and measure those different modes of motion. And you'd probably need different, more complex policy structures that could output appropriate force commands for those mechanisms.
So the current framework, while powerful for its target class, doesn't just automatically extend to any arbitrary complex mechanism without modification.
Correct. That's a defined scope limitation of the work presented in this paper. It's focused on mastering these fundamental single DOF interactions first.
That makes sense. You have to start somewhere, and these single DOF joints are incredibly common in everyday environments. Okay, so recap. The robot has approached the object, used its camera, found a grasp point, done its little probing dance, collected the trajectory, and successfully inferred the joint type. Let's say it decided it's prismatic, and estimated its parameters, the axis HP. Now what? Part 3, robot execution.
Right. This is where the robot actually takes that learned skill, in this case, and applies it to the real object, or maybe a simulated robot in a full physics simulation. The process involves a few steps we've touched on: perception and grasping, which we just covered using the camera and AO grasp P.
Gets the robot holding the object.
Yes. Followed by state construction, and then finally control execution.
State construction, what happens there?
This is the absolutely critical step that bridges the gap between the abstract, robot-free training world and the concrete, real-world robot interacting with this specific object. The robot takes the inferred joint type, prismatic, and the estimated parameters, the axis HP that it just got from part 2, the interactive perception,
Okay.
and combines this information with its current end effector position, which it knows from its own sensors. It uses these pieces to construct the object-centric state vector that the learned policy expects as input. In this case, it would calculate the current displacement along the inferred axis, EPS, and package it with HP to form the state HP.
Ah, okay. So the policy, which was trained on abstract states like direction of ideal prismatic movement and displacement along that direction, is now receiving inputs based on the real-world object's inferred prismatic axis direction and the robot's current displacement from the start point along that inferred direction.
Exactly.
This is how that learned skill, which was decoupled from any specific robot, can now be used by this specific robot interacting with this specific, previously unseen object.
Precisely. The real magic is that the policy doesn't need to know how those state values were derived. It doesn't care if they came from a perfect simulation model during training or if they were estimated just now from real-world sensor data and interaction. As long as the state information is formatted correctly, representing the object's inferred mechanics relative to the interaction point, the policy can use it to decide the next force to apply.
State constructed. Time to execute the control then.
Right. The robot selects the appropriate learned policy. In our example, it was PA, because it inferred a prismatic joint. If it had inferred revolute, it would load far.
Okay.
The selected policy takes the current object-centric state, HP EPT, and outputs the desired 3D force vector, F.
And the robot arm now needs to actually generate that force. How does it translate that desired force vector into actual movements or motor commands?
This is where a lower-level robot controller comes into play. Specifically, the FLEX framework uses an operational space controller, or OSC.
OST.
The OSC takes that desired force vector F that the high-level policy outputted, and it maps it to required changes in the robot's end effector pose, position, and orientation. These desired pose changes are then converted by the OSC and the robot's internal controllers into the necessary joint torques or joint velocities for that specific robot arm to achieve the target force application at the contact point.
So the OSC is acting kind of like a translator. The learned policy says globally apply this force vector to the object, and the OSC figures out the specific joint commands for this particular robot needed to generate that force vector at the contact point.
That's a perfect analogy.
And presumably the OSC can also handle other things simultaneously, like maintaining a stable grasp or maybe compensating for gravity acting on the robot's arm and the object's weight.
Exactly. The OSC is a well-established technique in robotics precisely for controlling the robot's behavior in Cartesian space, its end effector space, and applying desired forces or maintaining desired stiffness. It effectively manages the complex inverse kinematics and dynamics of the robot arm itself.
So this is where the robot's specific physics do matter.
Yeah.
But they're handled by a standard robust controller, the OSC. They're not baked into the learned manipulation policy itself.
Correct. That separation is absolutely key to the transferability. The high-level policy learns what force to apply to the object based on its state, and the low-level OSC figures out how this specific robot should move its joints to achieve that force command.
Okay, so the robot then applies this force continuously, recalculating the state based on its new position, getting a new force command from the policy, feeding that to the OSC, taking another small step.
Exactly. It loops. Perceive, state policy outputs, force OC executes force, object moves slightly, perceive new state, and so on.
Until the task goal is reached, like opening the object past that 80% threshold they use.
Yes, until some termination condition is met, like reaching the target joint configuration.
The paper does mention a limitation here, though. Something about the force magnitude.
Ah, yes. That's a crucial point for understanding the current scope of FLEX and where future work might go. The learned policy, remember, outputs a force scale, a value between 0 and 1.
Right.
That scale is then multiplied by a fixed maximum force magnitude, E eta, which was set during the training phase, likely based on the typical forces needed in the simulation environment.
So the maximum force the robot can apply is predetermined.
The maximum force the policy can command is capped by DIS. The crucial point is that the policy doesn't currently have a mechanism to dynamically sense factors like unexpectedly high friction in the real object, or maybe unforeseen weight or a strong spring resistance, and then decide on the fly to increase that base maximum force magnitude, or perhaps apply a much stronger initial pulse to overcome stiction.
So let's say the robot encounters a drawer that's just much heavier or stickier than the ones it was trained on, or the ones used to set. The policy might output its maximum learned scale, say 1.0, but if that resulting force, 1.0, still isn't enough to overcome the real-world resistance.
Then the robot could just fail to move the object, or it might stall out partway through.
It can't just decide, whoa, this is tough, I need to push harder than eat.
Precisely. The learned policy is optimal for the dynamics and force ranges it experienced during training. While the force direction learned in force space generalizes well because it's tied to the object's geometry, which the interactive step estimates, the absolute force magnitude required in the real world depends heavily on the object's physical properties like friction, mass, damping, springs, etc.
Which aren't fully captured by the initial probing.
Probably not fully, no. The current framework doesn't include a feedback loop for dynamically adjusting that maximum force based on real-time resistance sensing during the execution phase. This is definitely a clear area for future development, making the system more robust, not just to variations in object geometry and joint type, but also to variations in their physical properties.
Okay, so the framework is really elegant. Learn the object's behavior in this abstract force space, figure out the object's joint type through this neat interactive probing, and then execute the learned skill using a standard robot controller. It sounds great conceptually, but how well does it actually perform? Especially compared to existing methods, and particularly on those unseen objects in different robots. Let's dive into the experiments.
Right, the proof is in the pudding, as they say. The experiments were conducted in simulation using RoboSuite, which is a manipulation simulation platform built on top of the Myoko physics engine. Myoko is known for being pretty high performance and accurate for contact physics.
And what tasks did they test?
They tested the framework on a variety of pretty common sustained contact tasks involving articulated objects, things like opening cabinets, opening trash cans, the kind with a hinged lid, opening microwaves, and opening dishwashers.
A good mix of prismatic and revolute joints. And the objects themselves, were they just simple shapes?
No, they used objects sourced from the PartNet Mobility dataset. This is a large-scale dataset that includes a diverse range of articulated 3D object models derived from real-world objects. And crucially, for the main evaluation, they tested the system on objects that it had never seen during the training phase.
That's key for testing generalization.
Absolutely. The training itself was performed using just a small set of representative objects. I think it was one drawer model for learning the prismatic skills, and one microwave model and one dishwasher model for learning the revolute skills.
And during training, the system had access to the true joint information.
Yes, in the robot-free simulation used for training, they provided the ground truth joint type and parameters, but during the evaluation phase, using unseen objects and a simulated robot, the robot had to do the whole thing autonomously.
Meaning it had to.
It had to use its simulated RGBD camera, perform the interactive perception, the probing dance, to infer the joint type and estimate the parameters, decide where to grasp, load the correct learned policy, or R, and then execute the manipulation task using the OSC, the whole pipeline.
Okay. And how did they measure success?
The main success metric for these evaluation tasks was whether the robot managed to open the object to at least 80% of its full joint limit, either extension or angle.
And if it got the joint type wrong during the interactive part?
That was counted as an immediate failure for that trial. Misclassifying the joint means you load the wrong policy, which is very unlikely to succeed.
Makes sense.
It's also worth noting they actually set a lower success threshold, only 70% opening for the baseline methods they compared against.
Why lower for the baselines?
They mentioned doing this just to give the baselines a better chance at scoring some non-zero success rates, which kind of highlights how difficult this task actually is for those existing methods.
Wow, okay. And the paper also mentioned how they decided training was complete for FLEX, some convergence criterion.
Yes, for the FLEX policies, Papaninghar, they defined convergence based on performance over consecutive episodes. Specifically, the training stopped when the average cosine similarity, they called it CHUCH, between the applied force vector and the object's resulting movement direction was consistently high, at least 0.75 over 100 episodes in a row.
So JITCH is directly measuring how well the applied force is aligned with the actual motion it's causing. Highs means efficient force application.
Exactly. It's directly related to that cosine term in the reward function. They note that achieving this Jedwali 175 criterion consistently led to 100% success in opening the training objects in the simulation.
Okay, so they trained FLEX until it was efficiently manipulating the training objects.
Yep.
Now, who did they compare FLEX against in the main evaluation? What were the baselines?
They included several baselines representing different approaches. First, a standard end-to-end RL baseline. They used the same TD3 algorithm but trained it directly in the robot's action space specifically, training the robot's joint velocities to try and open the object, using camera images and robot state as input.
So the traditional robot-centric RL approach.
Yes. They also compared against CIPS. CIPS is described as a hybrid method that combines some RL for pre-manipulation phases with planning for the actual articulation part. Though in their specific setup for the comparison, CIPS started with the object already grasped.
Okay. And the third baseline?
The third was Gamma. Gamma is a relatively recent vision-based state-of-the-art method. It tries to infer the joint information purely from visual input, like video frames, and then uses planning algorithms for execution.
Okay, so 3 different comparison points. Pure RL, a hybrid RL planning method, and a vision-based inference planning method. Let's look at the results then. Table I in the paper shows the overall performance and training efficiency. What did it find?
The results are, well, they're quite striking, actually. FLEX consistently and significantly outperformed all of the baselines across every single object type they tested using those unseen objects.
Really? Across the board?
Across the board. For example, opening cabinets, FLEX achieved 91% success rate. The next best was CIPS at 51%. End-to-end RL was negligible.
Negligible like? 0.
The paper states its success rate was less than or equal to 0.01%, so effectively 0, yes.
Wow. Okay, what about other objects?
Trash cans. FLEX got 83% success, CIPS was down at 39%, and JAMA, the vision-based method, only managed 12% on the unseen trash cans.
That's a huge difference.
It is. Microwaves. FLEX was at 64%, CIPS at 45%. Dishwashers. FLEX achieved 78%, while CIPS was at 32%. The end-to-end RL was negligible on all of them.
That negligible success rate for the standard end-to-end RL, even after presumably a lot of training time, that really drives home the point about how challenging learning this kind of sustained contact task is if you just try to do it directly in the robot's own action space using conventional methods.
Absolutely. The paper implies it ran for 10 million time steps and still failed. It just seems unable to explore the vast action space effectively enough to discover a working strategy for consistently opening these things.
It vividly demonstrates the limitations of just trying to learn direct robot motion policies for these interaction tasks without a more structured approach like FLEX provides.
Exactly. Now, CIPS, the hybrid method, did achieve moderate success, definitely better than the pure end-to-end RL. But the paper notes it still suffered from unstable exploration sometimes. It could get stuck in bad states or lose contact with the object, which led to its lower success rates compared to FLEX.
And what about Gamma, the vision-based one? It performed well on some, but seemed to struggle particularly with the trash can.
Yes, the paper specifically calls out Gamma's difficulty with the trash can task in their experiments. They suggest it frequently failed to infer the correct joint type purely from passive visual observation of that specific unseen trash can instance.
So maybe relying solely on vision for joint inference has limitations when faced with significant object variations or maybe challenging geometry in novel objects.
That seems to be the implication here. The paper also mentions they needed to apply some filtering to Gamma's output because it sometimes predicted multiple possible joints, suggesting its inference wasn't always perfectly confident or uniquely accurate on these unseen objects. In contrast, FLEX's interactive probing seemed more robust for de-ambiguating the joint type and parameters, at least for these specific tasks they tested.
Interesting. So beyond just the success rates, FLEX also showed a massive advantage in training efficiency, right?
Yes, this is another really key result shown in Table 1. FLEX converged much faster than the learning baselines, end-to-end RL and CIPS. We're talking orders of magnitude fewer simulation time steps required and significantly less wall clock time for training.
Can you give an example?
Sure. For the prismatic policy used for cabinets, FLEX trained in under 1 million time steps and took less than an hour of wall time on their hardware. The end-to-end RL baseline, despite ultimately failing to achieve meaningful success, ran for 10 million time steps and took over 24 hours. CIPS was somewhere in between, needing more time steps and more wall time than FLEX.
And this huge efficiency gain links directly back to FLEX's core design choices, doesn't it?
Absolutely. Decoupling the training from the complex robot simulation makes each training step much faster. And learning in the simpler, lower-dimensional force space significantly reduces the amount of exploration needed compared to trying to navigate the robot's high-dimensional joint velocity or Cartesian space. The experimental results really strongly validate these benefits of the proposed framework, both in terms of final performance and the efficiency of learning.
Okay, so very impressive performance, much faster training. But the part that really grabs me, the one that I think has the biggest implications for practical robotics, is the transferability. The results shown in Table 2, where FLEX policies trained once could supposedly be deployed on different robot arms.
This is indeed where FLEX really shines and potentially offers a significant advantage over most traditional and even many modern learning methods. Table 2 presents the success rates of the exact same FLEX policies, which were trained using a simulated Panda robot configuration for these specific tests. Though remember, the policy itself is designed to be robot-agnostic when they were transferred and executed on different simulated robot platforms.
Which robots did they test the transfer on?
They tested on a Franca Emica Panda, similar to the training setup, a Universal Robots UR5E, and a Canova Gen 3. 3 distinctly different robot arms with different kinematics, dynamics, and control interfaces.
And the results. Did the success rates hold up when switching robots?
Largely, yes, it's quite impressive. For the cabinet task, the success rates were 91% on the Panda, 80% on the UR5E, and 86% on the Canova.
Okay, a small drop, but still very high.
Exactly, trash can. 83% on Panda, 73% on UR5E, 78% on Canova. Microwave, 64% on Panda, 52% on UR5E, 59% on Canova. Dishwasher, 78% on Panda, 71% on UR5E, 75% on Canova.
So while there's maybe a slight degradation compared to running on the robot model closest to the training configuration, which you might expect, due to differences in how the low-level OSC controllers are tuned or implemented for each robot, the performance clearly remains high and well within a usable range across these very different robot architectures. This feels huge. It seems to unequivocally validate that decoupling principle. The policy learned what force to apply to the object, and then the underlying robot-specific controller, the OSC, was able to successfully translate that into actions for each of these different arms.
Yes, and the paper explicitly states their belief that adapting the baselines like CIPS or maybe Gamma to new robot platforms would likely require significant retuning or potentially even retraining of robot-specific components, whereas FLEX's core manipulation policy is designed for direct transfer.
Why does this kind of robot-agnostic skill transferability matter so much?
Yeah.
For the future of robotics, what are the really practical implications?
Oh, the implications are enormous, particularly if you think about scaling up robotic deployments in the real world. Think about it. If you develop a skill for a robot, like opening a specific type of machine door or assembling a part, and that learned skill is tightly coupled to that specific robot model.
Then if you want to use a different robot later,
Every time you want to deploy that same capability on a different robot model, which happens all the time in diverse industrial settings, warehouses, logistics centers, maybe even future home environments where you might have different brands or types of robots you might have, to repeat the entire costly development, data collection, and training process. That's often prohibitively expensive and incredibly time-consuming.
So transferability like this could reduce development costs dramatically. You learn the skill once, maybe for manipulating a certain class of object, and it becomes like a reusable software asset that you can deploy across your whole fleet of robots, even if they're from different manufacturers.
Exactly. It moves us towards a world where you could potentially build libraries of manipulation skills, like a skill for open drawer, a skill for open hinge door, a skill for slide panel that could be downloaded and executed by any compatible robot as long as it has the necessary force control capabilities.
That would be crucial for getting robots into less structured environments, wouldn't it? Where maybe a single type of robot isn't suitable for all the tasks or spaces, or where an organization just happens to use robots from multiple vendors.
Absolutely. It's a significant step towards achieving true robot-agnostic task execution. It paves the way for more flexible, adaptable, and scalable robotic systems in the long run.
And they did include a real-world demonstration too, didn't they? Just to show it wasn't purely simulation.
Yes, they did present a proof-of-concept real-world test. They showed a UR5 robot successfully opening a physical drawer using the FLEX framework.
How did that go?
It seemed to work well in the video provided. Now, they did mention that the real-world demo involved some simplifications, for instance. They provided the robot with the known pose of the drawer beforehand, and they skipped the interactive perception phase for that demo, focusing purely on executing the pre-learned in policy.
Okay, so not the full autonomous pipeline, but still valuable.
Still a very valuable step, yes. It shows that the forces outputted by these simulation-trained policies, when translated into actions by a real robot's controller, the OSC, can indeed interact effectively with real physical objects. It suggests that the simulation, despite being abstract and robot-free, captured enough of the essential contact physics to produce policies that are useful in reality.
Okay, so summing it all up then. FLEX seems to represent a really significant advancement. It shifts the focus from learning specific robot motions to learning the object's behavior under applied force. This enables highly efficient training, strong generalization to new objects through that interactive perception step, and this really unprecedented transferability across diverse robotic platforms, specifically for these sustained contact manipulation tasks.
That's a concise and accurate summary, I think. It fundamentally changes how we might approach learning these dynamic interaction skills. By abstracting away the robot-specific mechanics during the core skill learning phase, and then relying on standard, robust control methods like the OSC for the execution on different platforms, it tackles some major hurdles.
Hurdles in generalization and efficiency that have, frankly, long plagued robotics manipulation research for these kinds of tasks.
Definitely.
Looking ahead then, what do the authors themselves identify as the next steps? Where does FLEX go from here? What are the areas for future research based on this work?
They point to several key directions in the paper. The first one, which we touched upon earlier, is incorporating dynamic force adjustment.
Right, dealing with that fixed maximum force.
Exactly. Extending the framework so the robot can somehow sense real-time variations in the object's resistance, like unexpectedly high friction, or the object being heavier than expected, or encountering a strong spring force and then adapt the magnitude of the applied force accordingly. Maybe modulating or having the policy directly output a force magnitude that accounts for sensed resistance.
So the robot could actually feel the stickiness of a drawer during the opening motion and decide to push harder if needed, rather than just giving up or stalling because it hit that predetermined limit.
Yeah, precisely. That kind of real-time reactivity to unexpected physical resistance would be key to making the system significantly more robust to the natural variations found in real-world objects. Variations that might not be perfectly captured in simulation or fully estimated during that brief initial probing phase.
That makes a lot of sense.
What else? Another area they mention is autonomous environment generation. Could the framework be extended to learn skills in even more varied or complex scenarios by having the system autonomously generate diverse training environments or tasks, perhaps based on some high-level goals?
So instead of just training on one drawer and one microwave, it could learn to generate thousands of different virtual drawers and doors with varying properties to train on, pushing towards more general-purpose robot learning.
Exactly. It moves towards enabling robots to acquire skills for truly open-world scenarios. potentially allowing interaction with a much wider range of objects and mechanisms, maybe even entirely novel ones that weren't explicitly designed into the training set.
Okay. Any other future directions?
And finally, they suggest exploring learning from demonstrations. Could incorporating human demonstrations or maybe teleoperated demonstrations make the learning process even more data efficient, especially for more complex tasks or objects where pure RL exploration might still struggle or take a very long time?
Using human intuition about how to apply force or wiggle something open could definitely give the robot a head start, couldn't it?
It absolutely could. Demonstrations might provide a valuable initial policy that the RL process can then refine, or they could illustrate nuanced force application strategies, like a slight upward lift while pulling a sticky drawer that might be hard for a purely exploratory agent to discover on its own. It could provide a strong starting point or constraints for the policy search, potentially reducing the need for those millions of simulation steps.
Well, this has been a truly insightful deep dive into FLEX. It really does feel like a genuine step forward in making robots more capable of interacting with the messy, variable, articulated objects that are just so common in all human environments, from homes to factories. That core idea of teaching the skill relative to the object rather than the robot, that feels like a powerful paradigm shift.
I agree. It directly addresses those fundamental hurdles in generalization across objects and transferability across robots, and does so with impressive training efficiency, which are all critical factors that have long held back progress in practical robotic manipulation for these kinds of contact-rich tasks.
So thinking about this, what does it all mean for you, the listener? Consider the implications here. What if robots could truly learn how objects behave when force is applied to them, in a way that's fundamentally decoupled from the robot's own specific mechanics?
Yeah.
How might that change the way we think about teaching robots complex interaction skills, moving beyond just task-specific programming or incredibly data-hungry robot-specific learning? And perhaps more excitingly, what previously challenging manipulation tasks, maybe those involving really subtle force control, delicate interactions, or unpredictable object responses, might now become feasible with an approach like FLEX. Could this unlock entirely new applications for robots in areas like manufacturing, logistics, service industries, maybe even assisting in our homes, interacting with our appliances and furniture in a much more natural and robust way? It certainly gives us a lot to think about.